Hi everyone, my name is Benjamin. I'm an assistant professor in data science at Entity-Embeddings in France. And in this presentation, I'm going to address processes and how to predict activities and timestamps in those processes using neural networks. So this work has been done jointly with Lockpicker, which is a French company providing process mining software. Even I know that the audience here know about processes. Let's, for the sake of the illustrations, present one. So a process is a collection of events, of ordered events that some entity follows in order to reach a final objective here. And we can notice that at some point in the process, most of the time, you have routing issues where one entity or another will take different paths because of different characteristics, because some routing rules. Already in here in this example, within the healthcare sector, we have medical decisions that have to be made in order to route the patient as best as possible, right? And no matter how you support your process, would it be with an information system, would it be just by hand, you might want to know in advance what will be those decisions, what will be those routing results, because you want to schedule in advance some beds, for example, or to prepare some resources and so on. And that particular task of knowing in advance falls into the area of predictive process monitoring. One of the different tasks of predictive monitoring aims at predicting the next event into a process execution. So you have what we call a prefix, which is just the summary of history and the current state your entity is in, and you want to know what will be the next event. An extension to that problem is the remaining activities prediction problem, in which you not only want to know what will be the next event, but also the one happening after that one, and so on until you reach the end of your process execution. We will call that the suffix of the trace of the sequence. Those are the main problems we are aiming at addressing in that paper, in that presentation, but also what we call the timestamp prediction problem. It's when will the next event be executed. So we want to know what is the next event and when it will be executed. Those problems have been addressed quite often in the literature, let's say in the 5 past years, and most of the most performing techniques used neural networks. Here is a snippet of the latest research work in that area, and we see that most of the most promising, let's say, techniques use what we call LSTMs, long short-term memory neural networks, which is a special architecture of network in which is embedded the ability to capture temporal sequencing, behavior of the sequence in order to maximize the quality of the prediction of the next event. Because in a process, of course, the next event is mostly driven by what has been happening in the past and in which order, which is one main ability of the LSTMs. But we saw other types of architecture, RNN, which is more generic types of LSTMs, which is recurrent network, CNN, convolutional neural network, mostly used on images firstly, but in this work the authors managed to transform the data set into some kind of image that they could use CNN on. Okay, so basically those types of architecture do well. Okay, they have good results, they're promising. So what's wrong? Well, neural networks, in their definition, it's already complex. You have a bunch of parameters to tune, hyperparameters to define, and RNN, LSTM, CNN, and so on add a new level of complexity to those architectures. So it's even more complex and maybe less adaptable to other situations, other datasets. So what we want to show and what we wanted to know, if it was possible to reduce the complexity of the prediction model. And to do so, our objective was to take this ability of LSTMs, for example, into capturing, behavior of the sequences, and to move that into the dataset. Okay, so we make the model simpler, but we still capture what makes LSTMs efficient, meaning the temporal behavior, into the dataset that we provide to the neural network. Okay, so we put that into the pre-processing phase. Also, there is a lack of consensus in the benchmarks used in the literature. Okay, people use different situations, datasets starts predicting a different position in the sequences. So it's hard to really say which technique is better. Even though LSTMs seems to be better, it's really hard to say for sure which techniques are the best. Also, there is no method that is able to provide a single shot prediction procedure, which means that in the remaining activities problem, what those techniques do is that they provide the next event, and then they embed the prediction into the new prefix to predict the next one, etc., in a recursive fashion, okay, until they reach the end of the sequence. What we want is, in a single shot, one prediction, the whole sequence. This would reduce a lot the number of predictions that you have to make, and this will remove, you know, this addition of error that you go from the first prediction to the very end. And lastly, there is no consideration of what we call in here parallel instances, meaning that sometimes in the process you will have overlapping activities. Some activity that starts before one ends, and this particular behavior is not taken into account in existing methods, and we want to provide the possibility to address those events. So the approach used the dataset, which is a collection of traces of sequences with history and with following activities, and at some point in time we want to stop, and with what we know about the sequences we want to predict what will happen next. This is the objective. To do so, the literature define two features, prefix and suffix, and we call a K prefix the first K event of a sequence. For example, in here, sigma, the 3 prefix of sigma is ABC, and the 3 suffix of sigma is what happened after the prefix, which is D in that example. Now we want to apply all of these concepts to parallel instances as well. So here, for the sake of the illustration, you have 4 types of parallel instances of behavior. It is mainly the definition of activities that starts before another one ends. Okay, so you have overlapping behaviors. It can happen differently, so perfectly on the same time frame, but also kind of switched. Okay, and it works in cascade, let's say. So if an activity C starts before B ends and D starts before C ends, the 3 of them are considered in parallel, right? It can also happen that D happens after B ends, and it's also considered in parallel, right? So you have different types of behavior that we want to capture. And to do so, we extend the definition of prefix and suffix in here, considering parallel activities, meaning that, for example, in sigma 1, the 2 prefix of sigma 1 is A, BCD, because BCD works as one. Okay, they count as one event because they are considered parallel instances. And by extension, the 2 suffix of sigma 1 is E, F, G. But you might notice that in these different situations, the knowledge of the trace at some point in time is not the same. What does it mean? For example, in sigma 2, you know that by the end of B, you know about C and D because both of them started, and the next event will be E. All right. In that situation, by the end of B, you only know about C, and you know nothing about D. So the next event will be D. Right. So in that situation, we say that the 2 prefix, considering parallel activities, knowing B of sigma 3 is A, B, C, because by the end of B, I don't know yet about D. Okay. And this particular feature is super important to predict the exact next activity and to know if this next activity will be in the parallel instance I'm in right now at the time of the prediction. And that is a cool feature. So the approach is to extract prefix from these data sets and to extract two types of features, topological features and temporal features, that we feed into classical neural networks based on two layers with dropout to improve the robustness of the prediction. And by the end of that network, we provide the prediction about the activities and the timestamps. About the temporal features, it's kind of classic. We try to get the minimum, maximum, some statistics about the duration of the activities, same statistics about the time between the events, and also some temporal features about the trace per se, the week of the day, of the month, when does the trace start, and the beginning and the end of each activity. So basic temporal statistics. What is a cool feature here is the capture of the topological feature. And without revealing the recipe, which is protected by IP, by lockpicker, you have to understand that we extract what we call a topological signature, which is basically a hash code of the chronogram, of the behavior of the prefix. And this topological signature embeds in its core what are the activities present in the prefix, how they are ordered topologically speaking, which means are they in a sequence, are they in parallel instances, and so on. So even though the prefix of two different chronogram can be the same, for example here, in here you see that the two prefix knowing C is A, B, C, D. Same thing as here, you see that topologically speaking they're not the same prefix, and you will see that the signature is not the same, which is super interesting to predict correctly the next activity. And what does the method do? It predicts the whole trace topological signature. It means that it doesn't only predict one activity per se, it predicts the chronogram of the whole trace. And starting from that, we can retrieve the next activity, the next one, and the one after that until the very end of the trace. So it goes two ways. From the graph, from the chronogram, you can go to the topological signature, and you can go back from the topological signature to the chronogram. It's a one-way, one-on-one translation. And that is how it works and the main core of our approach. So we wanted simply to test that approach, which is quite basic, on well-known datasets in process mining. So we use different parameters that I do not detail here because it's quite done empirically. And we use the benchmark inspired by Pasqua di Bisceglie and TAC because they use the same situations, meaning that we used 2/3 of the logs of the datasets for training, and we start the prediction at the second activity. I do not get into details about the results, which is not super important. What we wanted to show here is that mostly our approach is get similar results than the literature, if not better here, especially on the prediction of the activity, both in the suffix prediction and only in the next activity prediction. Two things have to be highlighted here is that for the suffix prediction, the metric that is used is the Damarol-Levenstein similarity distance, which is quite adapted to sequence comparison, but not so much for sequences that embed parallel instances. So we have to find a new one that will exactly show the efficiency of our approach. Second thing is that in the perspective of predicting the timestamps, classical neural network as ours is not that efficient compared to the literature and compared to the LSTM's techniques. So we can limit our approach by saying that so far LSTMs do provide better results in terms of timestamps prediction. So the statistics that we retrieve from the dataset is not enough to prove that classical neural networks can be at least as efficient as other techniques. So by this work, by this research, we could prove that there is a way to transfer the complexity of the predictive models into the pre-processing phase. First, it provides with a simpler architecture, easier to tune and easier to implement, and we can use in different situations. Here we propose prescriptive methods, descriptive also analysis that would already use the quality of this new data set, okay, we provide. We could also perform single shot predictions that we show with the topological signature prediction that include parallel instances prediction. That is all for my presentation. Thank you for attending, and if you have any questions, please reach me to my email address, benjamin.delmas@emsc.fr. Thank you.